Okay, let me give you guys a multivariable calculus optimization problem. So let's say you've got to design a box where you have to maximize the volume, but the condition placed upon you is that the length, which is this length here, the length of the box, plus the length of the girth. So the girth is defined as the perimeter of the cross section. So the girth is this length here. So you've got to design a box in such a way that it will give you the maximum volume, and you have to satisfy this condition. Okay, so we've done a similar problem to this in single variable calculus, but in single variable calculus, the condition placed upon you was that this must be a square. So that was in single variable calculus. So by placing that condition of it being a square, all you need is to change one variable. But now in multivariable calculus, you can vary two things. You can change the height, and then you can change this length here. So you could have a box looking like this. So you can change two things at once now. But in single variable, you can it has to be a square in single variable. Well, anyway, we are now at this stage. So design a box in such a way that that it will satisfy this and maximize the volume. So press pause and have a go. Okay, so to do this, we are going to vary x. So we are going to vary x. So this is x here. So this is x equals 1, x equals 2, x equals 3, and so on here. And we are going to vary y. Y equals 1, y equals 2, and so on. So this is your y, and this is your x. So if this is y, if this is y and this is x, then z will have no choice but to be a certain value. So we've got to somehow work out z, because it has to be the combination of the two has to be less than or equal to 108. So, but because we're trying to maximize the volume, let's take this to be its biggest, which will be equal to 108. So anyway, the girth is given by the height. So 2 times the height, which is this thing here, and then this length, 2 times this length here, which is this thing here, and then you times by this length, which is x. So so this condition can be translated to this. Okay, we are trying to find the biggest box, so ignore this, make it to be equal to the biggest value here. So that will then take us to here. Rearrange this, so the height is given by this. So so now we've got a situation where we can vary the x, we can vary the y, and then it will it will automatically work out the z for us somewhere in here, and then later on it will spit out the volume for us. So we are currently here. So so the volume is given by by this times this. That will then give us this thing here, which is this thing here, and then you times by the height of the box. You times by the height of the box, which is this thing here, which is this thing here. So the volume is given by this, and then let me tidy this up. So so if you tidy this up, it will then give you this. So we've got to find the critical points. So we need to partially differentiate this with respect to x. So that will then give us this, and then partially differentiate this with respect to y. That will then give us this. We are trying to find the critical points, so we need these two values here. So now now looking at this, you can see that y is in common, y is in common, y is in common. So factor out the y. So that will then give us one thing times another thing. And then looking at this, you can see x is in common, x is in common, x is in common. Factor out the x. That will then give us this thing here. So now we are currently here. Remember, we're trying to find the critical points. So critical points occur when this equals 0 and this equals 0. So so let's set this to be 0 and set this to be 0 to find the critical points. So now now we've got to find x and y in such a way that this whole thing here and this whole thing here equals to 0. So looking at this, you've got one block multiplying another block. Here you've got one block multiplying another block. Let's look at a case when y equals 0. So put 0 into here. Well, when you put 0 into the y, then this whole thing here will automatically be 0. Then if you put 0 into the x, then both of these will be 0. So one critical point will be 0, 0. So now remember, we are still considering when y equals 0. The other scenario is that this bubble here could be 0. So when y equals 0, we have to somehow make this bubble to be 0, because if this bubble is 0, then the whole thing would be 0. So we've got to concentrate on making this to be 0. So remember, when y equals 0, we can put 0 into here. So this whole thing here will then become this, meaning x must be 108. So another critical point is 108, 0. So far we've got two critical points, this and this. So the next step is to put 0 into here. So the next step is to consider when x equals 0. Well, when x equals 0, this whole thing here would be 0. Well, y could be 0, but we've already done 0, 0. So let's when x is 0, let's concentrate on making this to be 0. So when x is 0, we can put 0 into this x. So this thing here will become this thing here, meaning y must be 54. So another critical point is 0, 54. So we've got 3 critical points so far, and the last option is making this to be 0 and making this to be 0. If this is 0 and this is 0, then both of these will be 0. So our last option is make this to be 0, make this to be 0. So really we're trying to solve these two simultaneous equations. So let's multiply this by 2. That will then take us to here, and then get this, take away this. So that will then take us to here, meaning y must be 18. So if y is 18, if y is 18, then x must be 36. So somehow somehow solve these two simultaneous equations. Okay, so solving these two simultaneous equations will give us y equals 18 and x equals 36. So we've got another critical point, this one here. So as a summary, this is a critical point, this is a critical point, this is a critical point, this is a critical point. Hang on. So this is a critical point. If you put this into here, put this into the y, and so on, the volume would be 0. Put this into the x, put this into the y, and so on. The whole volume would be 0. For this critical point, the volume is 0. For this critical point, the volume would be this. And then we, from earlier, we can work out the height. Once we've got x and y, we can work out the height. The height is given by this. And by the way, when you get to this stage here, you should perform the second derivative test, because this could be a local minimum, meaning that you found the smallest box, the smallest volume. So you should perform the second derivative test to make sure that it is a local maximum. But take my word for it, this is a local maximum. Anyway, this critical point here will give us a volume of this and a height of this. So what that means is our box should have an x value of 18, sorry, hang on, an x value of 36, that's this length here, 36, y value of 18, so this is 18 here, and a z value of 18, so the height should be 18. So this box here will give us the biggest volume, okay, which will satisfy this condition, okay.